record on this computer. There we go. We are recording. We got a whole bunch of things to cover. And so if I, and again, the class is 60 minutes of class and then 15 minutes of QA. Feel free to put in your QA, your questions in the chat. I may or may not get to it. If I don't get to it during the lecture, it'll scroll up. I won't see it. So you might have to repeat your question when we get to the QA. Sorry about that. I'm trying to multitask, but I'm old and I sometimes miss things. Okay, so let's get started. Wait a second. I hit the wrong button. There we go. Okay, so here is the class schedule. Move that over there. We are in the third lecture. This class is divided into 3 sections. The first section is kind of the basics of physics and astronomy, and we're in the third lecture of that. There's 9 lectures in the beginning. The most intense part of the first section is when we talk about radiation, because that's really the core of being able to do astronomy. Because until 2015, everything we knew about the universe came from electromagnetic radiation, light, radio waves, and whatnot. Now that's all changed, but still the majority of the information we get comes from electromagnetic radiation. This course is called Stars and Galaxies. So the second section is about stars, not surprisingly. And that goes from lecture 10 to lecture 16. And then the third part of the course is about galaxies and the universe. So we're in the preliminaries now. Today, we're just going to cover a bunch of random topics. I'm going to go fairly slow. There are lectures where I go really fast. This is not one of them. I'm going to go fairly slow because the goal for this lecture is for you to be able to visualize the 3-dimensional view of our position in the cosmos, the way the stars go around the celestial sphere, things about magnitude, seasons, the moon rise and set, and it's all about trying to visualize in 3 space. So I've got a lot of simulations we're going to go through, and during this I'll answer the one question that came up about hold on a second. Got to make sure I mute before I blow my nose. Resume share. That's weird. Okay, let's try that again. Okay, so I forgot where I was. Let's just launch into this. So the celestial sphere is the name that we use for everything that we see. So here you are standing on the Earth. There's the Earth's spin axis. The celestial equator is aligned with the Earth's equator as it spins. If this isn't quite clear, we're going to go over this about 10 times today. The zenith is what you see directly overhead. So the zenith is specific to you. And the nadir is the opposite of the zenith. The celestial equator, like I said, is the extension of the Earth's equator as the celestial sphere spins. The north and south celestial poles are the extension of the Earth's north and south celestial pole. So here's a video to show that. So here is the Earth spinning. The ecliptic, and again, you're going to be, so there's noise in the background. Okay, tell you what, let me switch my video back. Hold on. Audio, go back to Yeti. Okay, how about that? How's my audio now? Okay, good. Let me kill this puppy. So the here is the Earth spinning, and the Earth spins on its axis. The ecliptic is the plane. Oh, kill this puppy. I'm so sorry. I meant turn off that audio input device. The ecliptic is the extension of the solar system plane, as we talked about last time. And so this is from the perspective of outer space. This is the exact same scenario, except from our perspective, where it looks to us like the stars are rotating around us, but in fact, it's the Earth that's rotating. Okay. The horizon here is our horizon. So we can see up, we can't see down. So it's literally our horizon as we go through. So the horizon, again, is specific to us, not specific to anything else. The ecliptic plane, which is listed here, is the plane of the solar system, except for Pluto. Well, Pluto's not a planet, but all of the planets exist in a flat plane, like a Frisbee. This is just terminology. The Earth rotates on its axis. It revolves around the sun, okay? And those are just the way that we will use the terms in this course. Sometimes people use those terms differently, but this is the way we'll use it in this course. The Earth rotates around its axis and it revolves around the sun. Cute joke. I didn't make this. So the ecliptic is parallel to the Earth's revolution around the sun. Yes, Travis, that's true, except more specifically, it's specific to all of the objects in the solar system. So all of the objects in the solar system revolve on the ecliptics because they're all revolving in a flat plane. Hold on. So if you can see my video, the solar system is like a Frisbee, it's flat. And so when we look at that flat plane, all of the planets and the sun and the moon all revolve along that line, the ecliptic. And I'm going to show you a bunch of other examples of that in a minute. So here is a picture from our perspective of the celestial sky. Now, of course, this is sped up. Normally, when you look out the night sky, nothing's happening. Unless you lie there for an hour, you can see that the stars do move. And you might notice here that it looks like the entire sky is rotating around like this. Yeah, I agree. The stars are so pretty. And they rotate around a central point there, which we call the North Star. Now, if you lived in the Southern Hemisphere, they don't have a South Star. They've got a problem. But we do have a star that's at that center. So if you can see here, yeah, I need to reset that. But that star right there, the area is pointing, is not revolving. Whereas these stars are rotating down, these stars are rotating up. So it's like the whole sky is rotating around a single point. And that single point is the extension of the Earth's North Pole as it hits the sky. The next video is also a time, it's exactly like the previous video, where we're going to advance time quickly so you can see the sky move, but it's a little different and will give you a different perspective. Watch this. So Caleb asks, is it possible to see the colors in space without special cameras? So I actually wrote an entire book on human color vision, so I could answer that in great detail. Like evolution has designed our eyes so we have very great color discrimination at relatively high light levels. And then we have a separate system, which a lot of animals don't have, which enables us to see at night, but that system is only black and white. And so it's very difficult for us to see those sorts of colors during the day because there's just not enough light. There's a second question is, if there was enough light, would we be able to see colors in space, and what would those colors look like? In other words, for example, what does the surface of Mars look like? That's a question without an answer. And the reason why is that physiologically, our brain does an incredible amount of color processing before it gets to our conscious level. And that processing deeply manipulates the colors that we see Long story. Anyway, that's a different course. Let's go on. So here what we have is a guy pointing north, south, east, west as the sky rotates around him. And then we're going to launch to a couple of visualizations. So here he's pointed south and the sky was rotating around him. Now he's pointed, well, we're looking west, although he's pointed south. And now we're pointed due north. And so when we pointed due south, it was like the whole sky was rotating. But now when we're pointed due north, it's like the sky is rotating around a point. Okay. So now the sky is lifting up, whereas when we pointed west, the sky was dropping down. And here it's just slewing from left to right. So again, this is from his perspective. It looks like the stars are all rotating, and they're all rotating around the point we call the North Star. But again, of course, this is an illusion. So let me bring up, shoot, where is that? Let me bring up new share. Okay. So here is what you saw. The guy is standing, and this is his horizon. And this is the way he looks at the sky. But now we're going to switch to the way it looks like to the outside world. So here he is standing on the Earth at about latitude 35.7, which is about where we are in Raleigh. And there is his horizon. Now notice as I go from latitude, there, latitude 0 to latitude 35, the angular distance from the horizon to the overhead is that degree there. So there's, I'm at latitude 35. We're going to switch back. So here is his horizon. If I go up, in this case, 37.7 degrees, there is going to be the celestial equator. And that was the homework question that you were asked about. So when you see angular distance, really just think of angle, okay? And that angle, in this case, is going to be identical to whatever latitude it is. So when you're at latitude 90, the North Pole is directly overhead. Then as we drop down, there we're at latitude 0, we're on the equator, and there it is. So let's go back. So again, the horizon is specific to me, and it's specific to what latitude I am on the Earth. And let's go back to the rotating sky explorer. And here it is again. There is the Earth rotating. We're at latitude 40. Let's change that to 30, 35. So here we are in Raleigh. The Earth is rotating around, but it looks like the sky is rotating around. And there is my horizon. And that yellow line is the celestial equator. Okay. So let's go back here. And this is a cute one. This will show the relationship of the ecliptic, which is the line that all the planets and stars are on, and the solar system. So here is the Earth. The Earth is spinning. It's revolving around its action, and it's also it's spinning on its axis, and it's also going around the sun. I'm sorry, it's revolving around its axis, and my gosh, I've even forgotten what the words are. What's the word for it spinning on its axis? Is revolve or revolution? Anyway, notice this purple plane is the plane of the solar system. And as it cuts through the celestial sphere, that is the ecliptic. And so the entire universe is visualized as this sphere, the celestial sphere that surrounds the Earth. Of course, that's just a visualization. It's not like that, but that's the way it appears to us. Okay, so let's go look at a couple other simulations here. Solar system scope. So here is a visualization of the solar system. Wait. Yeah, there we go. Here's a visualization of the solar system. We got Mercury, Venus, Earth, Mars, and notice when I go like this, it's completely flat. Okay, so let me get rid of some of this extraneous stuff. Let's hide the stars, hide the constellations, hide the grid. There we go. So we have just the naked solar system. So inside is the sun, Mercury, Venus, Earth, Mars. And the planets are grossly oversized. If we want to see them at real size, you really can't see them on this scale, okay? So Earth, Mars, so these all orbit, these are called the terrestrial inner planets. And then we have Jupiter, Saturn, Uranus, Neptune, and then Pluto is this weird one. Take a look here. Look how thin that is, okay? And that's the ecliptic. All of the planets except for crazy Pluto, which isn't even a planet, orbit in this plane. Okay. All the planets are actually in the same plane. If so, why? So, John, we showed that video last time about why the planets are flat. Basic, and I'll show it again in a little, in probably next lecture. So, rotate on axis, revolve around the sun. Thank you. Even I have trouble with that. For the southern hemisphere, do they have a star at the celestial south pole? No, they do not. That is a problem. Does horizon just mean the part of the celestial sphere parallel to where you're standing? That's exactly right. That is the horizon. The horizon is specific to you, where you are and what time it is, whereas the ecliptic is painted on the celestial sphere. The ecliptic does not change. Okay, in fact, I can show that right now. Oops. Share screen. So here is, let's advance this. So you've seen this a bunch of times. We got stars that are revolving around. It's just a nice simulation. We're going to put up, let's show the constellations here. And this, we're facing north, so it looks like the sky is rotating around here. If we faced south, it looks like the stars are scrolling like that. Okay, so let's face north. And what we're going to do here is show a grid, and this grid represents the celestial sphere. And the zenith of that grid, the top of that grid is the North Pole right there. And the whole sky revolves around this grid. There's a couple other lines that I want to show you. One line is that ecliptic. We'll show that there. Here is the ecliptic on that, and notice it's at an angle. The angle is actually 23.5 degrees, which is the angle between the ecliptic and the Earth's spin axis. So the angular distance from the northern horizon up, yeah, that just scrolled up. I'm sorry. Screen is frozen. Thank you. I'm so sorry. Yeah, apologize about that. Okay, so let me redo that. I'm sorry about that. So here is the sky rotating around. Of course, you don't see the constellation lines, but it does help. So we're looking north. This right there, it's very difficult to see, but this is the Little Dipper, where the handle is the North Star. The North Star is right there. Here, these stars there are the Big Dipper. There's the handle and there's that. That's one way you can find the North Star. Let me show you that again. Okay. The moon crosses the ecliptic when it revolves around it. So for us, I'll show you that in a second. Okay. So this is the Little Dipper. This is the Big Dipper, which is actually part of another constellation. That's the Big Bear there. But this is the constellation that we're most familiar with. There's this W over here, which is Cassiopeia, that you can also use to find the North Star. The Cassiopeia, that W, which is very prominent. If you just point from Cassiopeia up away from the W, you hit the North Star right there. Okay. So we've got those constellations. This grid represents the celestial sphere. Also on the celestial sphere is the ecliptic, which is this yellow line here. And you can see the ecliptic, the Sun, Jupiter, Pluto, Venus, Mercury, Neptune, Mars, and eventually we're going to see the moon are all on the ecliptic. Okay. Now there's a little bit up and down from the ecliptic because they're not all perfectly on that flat plane. And I think Forrest asked about the moon. The moon is also always on the ecliptic, although it is tilted, I think it's about 5 degrees to the Earth's orbit around the moon, and so orbit around the sun. So you'll see it pop a few degrees above and below the ecliptic. And there's the moon right there. And again, you can see the moon is on the ecliptic. So we've got the celestial sphere, which is defined by the Earth's spin. We have the ecliptic, which is defined by the solar system, and those are off by 23 degrees. We have a third line, which is this blue line, which is the plane of the galaxy that we're embedded in. Okay, so we've got us, we've got the angle that we are relative to our solar system, and then we have all that relative to the galaxy. So let me stop that and see if I can show you all this. So here's the Earth. Here's the plane of the solar system. And the Earth is at an axis to that solar system. And the plane of this solar system is actually at an angle relative to the plane of the Milky Way galaxy. Okay. So that's why this is a little confusing. We've got these 3 different angles here. So let's put the Earth down so it doesn't fly away and go back to the lecture. Okay, so that's the celestial sphere. Apologize for going over this 20 times, but is the ecliptic the celestial plane? No. The celestial plane is relative to the celestial sphere, okay? The ecliptic is the plane of the solar system. What is your favorite constellation? Orion, without a question. What are constellations used for? Well, constellations are used, it's like, why do we name gatherings of people? We name gatherings of people so we have an ability, instead of saying, oh, there's a bunch of gathering of people by this river with a little bend in it, we say, oh, he lives in Durham. It's just a way of identifying things. So constellations are there any places near Raleigh where you can see the stars very clearly? No. Probably, I'm sorry, what's the park next to the airport? Um, uh, anyway, I'll think of it. Olmsted, yes, Olmsted Park is probably the best chance in the area. You really can't see stars clearly anywhere in North Carolina, usually, unless a front has just moved through. And part of the reason for that are the coal-powered plants that are in the Midwest and in the Appalachians. And those coal-powered plants spread very fine particulate matter through the air. And so pre-industrially, the air quality in North Carolina, you could see about 70 miles, 70. Now the typical air quality, even on the clearest days, is about 10 miles. So you almost, up to the North Carolina-Virginia border is extremely good. So have any of you seen the Milky Way galaxy in North Carolina? Yeah, not North Carolina. So Amaris, I'm sorry, I've mispronounced that. Yeah, even using a telescope, it's not that good. I do have a couple of good telescopes that have image intensifiers that really do make a difference. You can see neat stuff there. Yeah, very slightly. When you go out west, especially in the mountains up west, not too high because then oxygen deprivation reduces your eyesight. The Milky Way galaxy is so incredibly bright, it's amazing. So anyway, we talked about how to find north. A constellation is a pattern of stars. There's 88 constellations in the sky. And the thing is, the constellation is just the way it appears on the night sky, not the way it really is. So let me show you something about the Milky Way galaxy. I'm sorry, about the Big Dipper. So here is the way the Big Dipper appears on the night sky. Here are the stars, the little black dots are the stars that make up the Milky Way. If we go over to the side, we see those stars are at various distances. They aren't necessarily even related to each other. And so the constellations are made up with how things appear to us, but they don't necessarily represent any real clustering of stars. I could slightly see the Milky Way at Oak Island. That's impressive. The nights are really clear there for some reason. Yeah, it must be the airflow kind of keeps that polluted air out of the way. Yeah, so I remember seeing the Milky Way galaxy outside Santa Fe at a resort when I was there, and it was just spectacular. You can see the Andromeda galaxy, which is 2 million light years away. And Appalachian Mountains, definitely you can see them better there. Yeah, I could see a band very faintly, but I tell you, when you see it for real, it just will blow you away. Okay, so let's go back to presentation. And now we talk about angles on the night sky, and I apologize for the confusion in that question where they say angular distance. We will often use angular distance, really just replace that with angles. And we measure angles with degrees. You're all familiar with degrees, 360 degrees in a circle. But astronomers use a couple other measurements. We use a degree, and 1 degree is about half of a thumb at arm's distance. Okay. In this one, they're saying a pinky, but your thumb, your pinky, figure, a degree, 2 degrees, somewhere in that range. You divide the arc, the degree into arc minutes. So there's 60 arc minutes in a degree. And each arc minute is divided into 60 arc seconds. So there's 3,600 arc seconds in a degree. So the sun and the moon are about 30 arc minutes, about half a degree. So your pinky can typically cover the sun or the moon, or depending on your hand and the length of your arm, it might take your thumb. But one of your fingers can cover the sun and the moon. The fact that the sun and the moon are about the same size on the horizon is kind of unusual. So 30 arc minutes or half a degree for the sun or the moon. Your eye has a resolution of about 1 arc minute. Okay, so you can see objects that are separated by 1 arc minute, by 1/60th of a degree anywhere. And then we read with that, that's considered 20/20 vision. And so when you look at the moon, you can resolve about 30 pixels across the moon just with the naked eye. Okay. A typical telescope can see about 1 arc second. In other words, they can separate objects on the sky that are separated by about 1 arc second. So about 60 times better than just the naked eye vision. And most telescopes cannot do any better than that, just because the atmosphere really messes up light. And we'll be talking about that when we talk about telescopes. But these are things you have to know for this course. Degrees, how big the sun and the moon are in terms of angular distance, the angular distance or angles, which is about half a degree or about 30 arc minutes. Human resolution is about 1 arc minute. Telescope resolution is typically 1 arc second. Okay. Stellar magnitudes, we'll be coming back to this over and over in this course. This is your first introduction to it. So there's some bright stars and there's some dim stars. That just is the nature of stars. And they're ranked, and the ancients ranked these stars. And what they said is, first magnitude stars were the brightest stars in the sky. Sixth magnitude stars were the dimmest stars in the night sky. So first magnitude stars were really bright. Sixth magnitude stars were really dim. And again, this was a system that was created thousands of years ago. Modern astronomy has adopted this same system, except they put some mathematics behind it. And because this is a historical system, the mathematics get a little weird and they get very unintuitive. So I'm going to go over this slowly, even though it seems simple. So here, first magnitude, where my cursor is, are the brightest stars in the sky, except it's no longer true. The brightest star in the sky is Sirius, and Sirius is magnitude -1. Okay, so this is where things get a little weird. Sixth magnitude is really dim. First magnitude is really bright. But there are things that are even brighter than first magnitude. And so the scale goes up and it goes into negative territory. So the full moon is magnitude -13. The sun is magnitude -28. Okay. So negative magnitudes are really, really bright objects. And because we are no longer limited to human vision, we can use telescopes. The scale often goes down to very dim stars. So for instance, the Hubble can see magnitude 30 stars. And so the dimmest stars in the night sky are really big positive numbers. The brightest things in the night sky are really big negative numbers. It's, as I said in a previous lecture, astronomy is a historical science, and that means we get a lot of really bizarre things about it. Do we need to know the math or just the concept? So John, you definitely need to know the concept of magnitudes. I'm going to show you the equation in the next slide. You're not going to have to memorize that equation. You are going to have to memorize a couple of things about the equation. I'll show you that in a second. So here's the equation. You do not have to memorize this equation. Okay. So here is a magnitude 0 star. This is something you will have to know. If the difference in magnitude is 5, the difference in the actual luminosity, how much radiation is produced, goes by a factor of 100. So every magnitude 5 difference in the scale, so the difference between a magnitude 0 star and a magnitude 5 star is the magnitude 5 star, magnitude 0 star is 100 times brighter than the magnitude 5 star. That is something you will have to know. Okay. So magnitude 10, you've gone down by 2 orders of 5. It's now 100 times 100 times 10,000. And this is a logarithmic scale or an exponential scale. Okay. So if we go down by a factor of 15, so the difference between a magnitude 0 star and a magnitude 15 star is a factor of 1,000,000 to 1. Okay. So the difference between the sun's brightness and the dimmest star that the Hubble Space Telescope can observe is, a quintillion to 1. Okay. So because it's an exponential scale, it covers an extremely large range of luminosities. And you will have to know that a difference of magnitude 5 is a difference of 100. Okay, so here we've got a pole. Let me bring up the pole. So star X has an apparent magnitude 3, star Y has an apparent magnitude of 8, which is true. A, X is 5 times brighter. B, Y is 10 times brighter. C, X is 100 times brighter. D, Y is 50 times brighter than X. This generic pole has an E, just ignore that. Very good. So most of you got this right. Because the difference in magnitude is 5, star X is brighter because it's got a lower number. Star Y is dimmer because it's got a bigger number, a bigger positive number. And the difference is 5, so the difference in luminosity is a factor of 100. Okay. So let's show a couple of simulations here. You share. Nope, let's show the other one. Okay, so brightness, we've got the luminosity, how much energy the star is putting out. But when we see a star in the night sky, we don't know if it's close or it's really bright. And so here, both the truck and the bicycle seem at approximately the same brightness, but the truck is much farther away. And so without any a priori knowledge, we don't know whether it's bright and far away or dim and close. Okay, we just don't know. So we have this dance between how bright things appear, how far away they are, and how luminous they really are. And we're going to be going into this in excruciating detail. But let me show you one example of that here with the simulation here. So here we have 2 light bulbs. The light bulbs are both at 25 watts. And this number here, that 1.989 refers to a reading of the luminosity that's being recorded by this sensor right there. Okay. And as I move the sensor away, you can see that the brightness that's recorded goes down. Okay. So here we're at 1.989. But I can also change the wattage here of the 2 light bulbs. So I'm going to change the wattage of this light bulb to 100. So this is 25. And as I do so, notice that the luminosity reading goes up from 1.989 to 7.958. Okay. So I'm going to ask you and put your answer in the chat. How far away should I move this sensor on this lower one so it matches the amount of luminosity coming from the 25 watt light bulb? So I've moved this to 100 watts. So it's 4 times more powerful. Oh, okay. So most people would think 2, but let's go to 4. I go to 4 and it's 1.989, But here, if I go 4 times away because I increased the luminosity by a factor of 4, look, it's at only 0.498. So why is that? Okay. It's because the luminosity drops is 1 over the distance squared. So I'm saying that in words. We're going to be going over this in detail. And so the correct answer is 2. Okay, I can't quite get it perfectly. There we go. Close enough. So so I increase the luminosity by a factor of 4. I increase the distance by a factor of 2. So 1 over the distance squared is the difference in luminosity. Okay. So if this is not intuitive to you, put a bookmark in your brain about that, because we're going to be going over this over and over again, because this is critical for us trying to figure out where the stars are, how far away the stars are, and what the shape of the Milky Way galaxy and what the shape of the universe is. Okay. So let's go back to the lecture. Seasons. Why are there seasons? Any guesses? So what was the formula again? Nikki, the formula is 1 over the distance squared. It's in the formula file that's in resources, but don't worry about it now, because we're going to be covering this in mind-blowing detail in the next few lectures. So Micah, no, I did not use the formula. That formula is really talking about the magnitudes, which is a logarithmic scale. When I was showing you the brightnesses, that was just talking about the luminosity directly. Earth's tilt causes the ray of light from the sun to hit the Earth at different angles. That's correct. If you poll most people get this wrong, though. So the Earth orbits around the sun, and it does get closer and farther away. And so we ask a general population, not NC State students, obviously, because you guys are smart, but if you ask a general population, they're going to say, oh, well, it gets cold because the sun gets farther away. Well, the sun does get farther away in July. It's farthest away in July, and it's closest in January. Okay. So they're completely wrong. It has nothing to do with the fact that the Earth's orbit is elliptical around the sun. It does get closer and farther away. So there must be another reason.
You know that Earth orbits the sun, right?
So Camille, I'll be covering the lunar
a full year for our planet to complete
phases
its orbit.
just immediately after this.
Earth also rotates like a slightly tilted spinning top. Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer, and the sun stays in the sky much longer. Notice, too, that while it's summer in the northern hemisphere,
yes,
it's winter in the southern hemisphere. Because of Earth's tilt, the seasons are reversed. We observed how Earth's tilt creates the different seasons throughout the year. How does this affect life? Plant life and other photosynthesizers, we call them primary producers, depend on sunlight. They respond to the changes in the seasons. Earth-orbiting satellites measure the amount of carbon dioxide absorbed by these primary producers. Bright regions on this map show where they devour the most carbon dioxide, turning light from the sun into oxygen and natural sugars. In spring, when sunshine strikes the cold waters of the North Pacific, productivity skyrockets. Phytoplankton and other microscopic photosynthesizers form the base of the ocean food web, and all ocean life responds to changes in the seasons. On land, forests grow green during the spring, brightening the continents. During winter, continents in this view turn dark from a lack of photosynthesis.
So there's three causes for the seasons. One is the fact that the sun's rays are more direct. The second is the fact that the sun is just in the sky longer. As you can see here by up here at approximately 40 degrees latitude, we have more than 12 hours of sun during the summer. The third isn't mentioned and you're not responsible for. The third reason is that in the winter, the sun's angles come in at an angle and it goes through more atmosphere. And so there's more extinction of the radiation. But just you don't need to know that. So let's show a couple more videos. Seasons ecliptic. Hold on. Okay, seasons ecliptic. And so here it is. As the Earth goes around, the spin axis stays pointed in the same part of the night sky always. But as the Earth goes around, the sun's angles, as you see from here, observer latitude. Let's change the observer latitude. Okay, so let's go up to Raleigh, which is about 35 degrees. Okay. And by the way, the sun is never overhead in Raleigh. It's never overhead because the sun angle can only get up to 23 degrees, which is the tilt of the Earth's axis, and we're at 35 degrees. Do we look at seasons at other planets? Oh, most definitely, yes. And so planets that have the spin axis directly up and down relative to the ecliptic do not have seasons. We have one planet, Neptune, I believe, who has it, the spin axis actually at 90 degrees. And there they have just obscene seasons. Then there's the case of Mercury, which is almost tidally locked to the sun. So doesn't really have seasons per se. It's just one side's hot and one side's cold. Okay. And so let's see, and sun motions. And here's another one. And so here the celestial sphere is rotating around the sky. Okay. And so the yellow line is the line that in a particular day, the sun draws on the day sky. The sun, rises in the east, sets in the west. But now as I change the time of year, so let's go to December. Now the white line is the ecliptic. And now the sun is in the lower part of the ecliptic. And so now the sun still rises in the east and sets in the west, but it does so at a much lower part, much more towards the southern part of the sky. Okay. So again, as you can see, the sun is in different parts of the ecliptic. And so here in the middle of summer, it's very high. Okay. Does the moon orbit the Earth in the same plane as the planets orbit the sun? More or less, yes, Matt, but Micah is correct. It's there's about a 5-degree tilt. So it's a little bit of a tilt. And we'll get into that in great detail in the next lecture when we talk about eclipses. Okay. Anyway, I really like this animation because it shows the sun moving on the ecliptic and at different and then it traces out in a particular, so it moves on the ecliptic over a year, and it moves across the night sky over a day. But where it moves on the on the day sky depends on where it is on the ecliptic, which is in various parts of the year. Okay. If the Earth didn't rotate on a tilt, would it be less inhabitable? So I'll get into this in the last lecture of the course. The Earth's tilt has been incredibly stable for 4.5 billion years. Without the large moon that we have to stabilize the Earth's spin, the Earth's spin would have been chaotic, and it would have created a very chaotic environment, a very chaotic ecosystem, and most people think that advanced life could not have developed in that situation. Okay, so back to the lecture. So there's the season, and there's the season in winter. And here is a picture of the Earth. There's a spin axis. Why don't we have eclipses? Yes, so we'll be getting into that. That's a good answer, Micah. Okay, so there's the Earth spinning. What season is it in the Northern Hemisphere for this picture we're seeing? Is it winter, spring, summer, or fall? Okay, so most of you chose winter. So that is wrong. You look at the tilt, the axis of spin is directed directly towards us. And so that means this is summer, okay? So we're looking at it, and there's more of more of the Northern Hemisphere. You get more than 12 hours of daylight in the Northern Hemisphere because the spin, the Northern Hemisphere, the North Pole is directed towards us, okay? So here is another one, and now we see the spin axis on the side, and let's ask the same question. Oops. What season is it in the Northern Hemisphere? A, winter, B, spring, C, summer, D, fall. Okay. And again, most of you thought it was winter, and that is just wrong. It's going to be either spring or fall, and in fact, it is it's spring. And let me show you why. Go back to this. Okay. So here is the Earth, and as it's going to right there, the spin axis is directed. Notice that the spin axis is pointing towards the sun. So that is summer, and over here is winter, where the spin axis is pointing away from the sun. So what you saw in that first image was a spin axis pointing towards us, and so that would be summer. Now here, the spin axis is pointed to the left, That's going to be fall, winter. And here, from the perspective of the sun, the spin axis is actually pointed to the right, which is what you saw in that second question. And that would be spring. There's summer, fall, winter, and then spring and summer again. Okay. So just take a sun and an earth, take a light bulb and a spinning ball, rotate at 23 degrees, and just play with this to get this idea. Now, that second question, I'm not going to have you figure out whether it was fall or spring. That's a little confusing. But most definitely, when you look at an image, you should be able to tell whether it's winter or summer in the Northern Hemisphere, and whether it's spring and or fall if the axis is tilted sideways. Yeah, so this course, this lecture is all about visual learning. There'll be other lectures that won't be as visual. This is probably the most visual. Well, I take it back. The next lecture will be just as visual because we'll be talking about eclipses. Okay. So you're just going to have to sit there with a couple of balls and just play with it to really make sense of this. Okay, I'm not a big one for solstices. Moonrise and set, let's get into this. So you've seen this video, this image before. The Earth is rotating. Again, everything rotates counterclockwise by convention and we're looking at the solar system from the top. So the moon rotates, revolves, does one of those R words around the Earth, while the Earth does its R word around its spin axis. So the Earth spins counterclockwise here. And so there you are, the moon is directly overhead when it's noon and it's new. The moon is directly overhead at sunset when it's at the first quarter, and so on and so forth, okay? And here's the sun is off here someplace. And here's what the Earth looks like from the moon, and here's what the moon looks like from the Earth. I always get revolves and rotates confused. I'm so sorry. We're going for a spin, that's right. And what's even more confusing is that so the phase of the moon as it goes around kind of makes sense. It's continually going from the different phases. But the moon will be in different places in the night sky depending on what phase it is. And that's what kind of throws you. And so here is looking at south this is at sunset. Here are the various positions of the moon at the various phases. So we go from new moon, and you are responsible for the different phases. New moon, a waxing crescent, first quarter where we see half light and half dark, a waxing gibbous, full moon where the moon is completely full, waning gibbous, third quarter, and waning crescent. So as it gets bigger, it's waxing. As it gets smaller, it's waning. And when it's tiny, it's a crescent. When it's really big, it's gibbous. Okay. So new, waxing, crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent. Okay. And again, its position is going to be dependent on where you are. So when you have a question of the moon is at first quarter and it's 6 p.m., where is the moon? Well, it's going to be directly overhead. Okay. So at noon, where is the moon if it's first quarter? Well, it's going to be right on the horizon. If it's noon and the moon is full, where is it? Well, it's not going to be visible to you. Okay. So if you can just visualize this graphic here, I can, if I ask a question of where is the moon, if it's in this phase, what at a particular time, you can always kind of figure it out by drawing the horizon perpendicular. So at midnight, if the moon is fullest directly overhead, at midnight, if the moon is first quarter, it's going to be on the horizon. If midnight, if the moon is a waxing gibbous, it's going to be at about, halfway up the night sky. And here are the phases at sunset. Okay. So let's show a couple more simulations and then it'll be time to stop. So lunar applet. So there's sunlight. Here are the phases as seen by this guy here. And there is the position of the moon and of the sun on the night sky. And see, as the moon goes around the earth, the disk between the moon and the sun increases continuously. And so when the moon rises and sets, well, it might change by actually 15 degrees every night. Yeah, so Josh, the size of the moon actually does not change. It's an optical illusion, and there's no definitive answer to why we have that optical illusion. Are these animations available to us, or do you have links to visuals like this we can use? Yeah, that's a good question. These are all Flash animations. I've got a Flash viewer. I can bundle these up and put it as a PDF as a zip file in the resources on the website. But you're going to have to find your own Flash visualizer. Everybody did these in Flash, and Flash no longer works on Macintosh, so I had to get a third-party program. It's called L Media to show these Flash simulations. Okay. When the moon hits your pie like a big pizza pie, that's amore. Yes. Let's see, moon bisector. Here's another cute one. There's the moon sun direction. There's the sun bisectors. There's the shadows. And the moon position. Okay. So I'll bundle these up as Flash animation so you guys can play with it. It looks like I'm out of time. So let me stop the share and I'm open for questions. Either put it in the chat or open your mic. That's fine. Thank you. Questions? Again, I apologize if I didn't answer during the lecture. When it scrolls up, I lose sight of it. Can you explain the angular distance is always the same as the latitude? So the angular distance from the equator to the celestial equator is going to be, so when you're on the equator, your horizon, the north and south poles are going to be on your horizon, and the celestial equator will be directly overhead. And so the angle between your 90 degrees and the celestial equator will be 0. As you go up in latitude, that horizon changes, as we saw in that video. Let me bring up that simulation again. Yeah, here we go. Share. Okay, so here is your horizon. Okay, and so let's say you're at latitude 0. Close enough. So the notice that the poles are on your horizon. The celestial equator is directly overhead. And that relates to, Here is your horizon right there. And there's the Earth spinning around, and there's the celestial equator. If we go to 35 degrees, there is the horizon, and there is your equator there, and there's the celestial equator, and the angle between those two is going to be 35 degrees. So Peter asks, what causes the northern lights? The northern lights are caused by the solar wind, highly charged particles that slam into the Earth's magnetosphere. The Earth's magnetic field stops those particles. Those particles then spin down the Earth's magnetic field until they hit the Earth's magnetic north pole. And when those extremely energetic charged particles from the sun hit the Earth's atmosphere, they ionize the Earth's atmosphere, producing that glow. Have any of you seen the Northern Lights? I've seen them twice in Minnesota. What's the difference between different kind of moons, like harvest moons, blood moons? I don't know. I think one of them, blue moon, is where there's 2 moons in 1 month. That's just a calendar thing. It's really not astronomical at all. The others, I don't know. Can a star turn into a planet? Kind of. So the definition of a star is an object that has thermonuclear fusion happening at its core. So Jupiter, for example, does not have thermonuclear fusion at its core, but if Jupiter was 2 or 3 times its size, the center of the Jupiter would be hot enough to start those reactions, and it would turn into a star. Conversely, when a star has burned out all of its fissionable material, so it no longer has that thermonuclear reactions going off, then it's a dead star, and we call it a white dwarf. And you could also call a white dwarf a planet, because it isn't really a star anymore. Why does everything revolve counterclockwise? So partly that's convention, because by convention, we're always looking at the solar system from the top down. But also, if there was anything in the solar system that was going around the solar system in the opposite direction, the very first thing that would happen was it would slam into something that was going the other way, and it would destroy that object. And so once a solar system, any solar system, has decided on a particular direction, anybody that goes against that direction is going to be quickly destroyed. And that's why all solar systems in the entire universe always revolve around in a single direction. If a star is super bright, does it mean it's closer or just has a higher magnitude? Pierce, the answer is yes. We have no way of knowing without additional information whether a star is close or really bright. And so that additional information is what we call the distance ladder. We try and figure out the distance to the object independent of its brightness. Once we know the distance through parallax or spectroscopic parallax or other mechanisms, then we know how intrinsically bright it is. And knowing how intrinsically bright stars are is really critical to our understanding of the way stars develop. How fast is the Earth moving per second? Good question. You could probably Google it. I'm going to guess it's about 15 or 20 kilometers a second. Let's see how close I am. How fast is the Earth? In its orbit, 30 kilometers a second. I said 20, so that's not too bad. So the planets are all on the same plane, but that does not include Pluto, Sirius, dwarf planets. Why is that? Yeah, so those planets, they still orbit in the same direction. They're just at a much higher angle. That's because they've had very close interactions. We think that Pluto had a close interaction with Neptune millions of years ago, and that close interaction popped it above the plane. And so that happens with the other dwarf planets. When they get too close to, say, Jupiter, they'll pop up and down. If a star is super bright, does that mean it might explode? Absolutely, yes. We have 2 lectures covering that. And when they explode, they go in what's known as a supernova, when they're brighter than 1 billion suns. And if a supernova went off close to us, like within 50 light years of us, that would be the end of life on Earth. So let's just hope that doesn't happen. Isn't the sun also revolving around the center of the Milky Way? Yes, it does. So everything's revolving around everything. So the Earth is spinning on its axis. The Earth is revolving around the sun. The sun is revolving around the center of the Milky Way galaxy. And the Milky Way galaxy is moving through the universe at a certain speed. So we've got all these speeds, and all speeds are relative. What does the galaxy revolve around? So our galaxy revolves around its spin axis, which is the supermassive black hole at the center of our galaxy. And it takes about 200 million years to do one revolution around our galaxy. But we don't think that it's revolving around anything in the universe. We do know that it is moving relative to the universe at a few hundred kilometers per second. Is the galaxy slowly being swallowed by the black hole in the middle? So, Louisa, many people think so. The answer is no. The reason why is we have a really tiny supermassive black hole. It's only the mass of 4 million of our suns. And we think it's going to eat a star in the next few years. It's really not that hungry. We do have other galaxies, such as M87, that have supermassive black holes that are like 4 billion solar masses in mass. But even if they're 4 billion solar masses, this black hole itself is really, really tiny. Like our black hole is really only comes to the orbit, I think, of Mercury at the center of our galaxy. So even though it's really massive, it's really small, and it's really hard to eat a lot of stuff. How do black holes grow larger? Through consuming things. That's exactly right. The event horizon, we have 2 lectures on black holes. The event horizon gets bigger as it consumes more stuff. We do not have a good theory for why supermassive black holes exist. We just don't know. There's just not enough time for them to exist. We do know that they're critical to the evolution of galaxies, and we'll be talking about that more later in this course. Other questions? Okay, let's wind up. Thank you so much. I will see you, everybody, on Thursday. And don't forget, if you have problems getting into WebAssign, I sent you all the Zoom address. So please go to that Zoom address today to get your get access to WebAssign. That's our account rep. He's several higher levels up from the tech support guys you've been dealing with. So definitely take advantage of the Zoom address I sent you this morning. See you guys on Thursday. Thanks so much.
Thank you.
Thank you. Sure.
Thank you.
Thank you.